this chapter is about Monte Carlo methods, which involve sampling from an environment, from like some kind of thing that can simulate an environment. And this is useful for problems where we don't have an explicit model for the environment. Like in this chapter, it was all about the dynamic programming chapter was all about environments where we have this probability transition function, where we have an explicit probability for every transition that we would see. And that can be used to calculate a lot of stuff. But in this chapter, we are assuming that, well, I guess there's not really like a picture here of it. We're assuming that the only thing that we really have is the ability to interact with the environment and collect like returns or, what will be called trajectories in the environment, which are just a set actually here. So in this like pseudocode box, this is the information that we have access to, which is there's sort of three things. There's the states, the actions, and the rewards. And we have sort of a list of those until termination. And for the purpose of this chapter, we're pretty much only considering environments where there are episodes that will terminate. So like the agent will make decisions, take actions in the environment, and then at some point, like it'll reach a terminal state. And one of the first example used here is the Blackjack example. And in Blackjack, the terminal state is just the end of that hand, where the player will either, win, lose, or draw with the dealer. So we went over this, like the chapter defines, a bunch of the rules for Blackjack. And the action space only has two actions. The player can either stick or hit. And if the player goes bust, meaning like he has a card count exceeding 21, then the episode's over. Or if the player decides to stick, the episode is also over because there's no other action to happen. So for this, the point, one of the points made here is that it is easier to write a program that simulates this and just generates a particular outcome for the game than it would be to calculate this probability transition function for Blackjack. So like, Dimitri is here. Okay. So also like in the previous section, so like for the dynamic programming section, where do I have? I have something like in terms of like actually implementing this, I have something that like defines like a Markov decision process. So like for the previous chapter, the Markov decision process, like we always have the state space, the action space, the reward space. And in this case, like these are all finite and they're small enough that it's like manageable on a computer. And then, like really like these four things are what are necessary for this these MDPs, and they're like, this is the probability transition function, and you can represent it a lot of different ways. Here it's like a 4-dimensional array because there's 4 inputs, but it contains all of the probabilities. And now in this section, instead of that, I still have the state space and the action space. Actually, like another difference here is like I also have all the rewards like known ahead of time. And here, we don't actually need to know the rewards ahead of time because it's kind of replaced by some kind of simulator. And here, like the simulator is some function, and you have to initialize it with a state action pair, like the way I wrote it. You could also just pass it a state and a policy. So, we are interested in trajectories that are created by some policy in the environment, and the policy is what selects the actions. So the simulator is just going to take the action given by the policy and then generate a trajectory. And these other things in the struct are not really that important. They're just kind of convenience functions to have for later on. But the main difference here is that there is no longer a reward, because so this simulator will then provide the trajectory here by basically telling you what the updated state is and then what the reward is, if any, for that step. So the function is now going to give us the reward as opposed to the reward being like an explicit list of things that we know the probability of each reward. Now all we can do is sort of observe what happens with the trajectory. And the idea here, so the first section is we start with just like, how do we then predict the value function for a policy? And that's what we did in the previous section too, where like prediction is a little easier. And, this is a pretty simple algorithm because all the rewards we obtain are, unbiased estimates of the reward under the policy. So we can actually just calculate the discounted future reward. In this case, I'm also like, this happens going backwards because it's easier to calculate G going backwards because you can accumulate all the discounted rewards as you go by continually multiplying by the discount rate here. And then all we have to do is average all the observed returns at every state. So we basically, have a value function, which is just a list of our value estimates at every state. And every value estimate is just an average of the returns. Now, like actually averaging the list is not what you really want to do in practice. Instead, you can calculate the average incrementally, like we did in the bandit chapter. There was a lot of information about that. But here, I mean, I have a version of it here where the update to the value function, you can see that this line does the incremental update of the average. Well, you do have to maintain a count to do this. So every state has a count, which keeps track of how many times we visited the state. And then G is the reward that we're keeping track of, like inside of this episode that has been simulated. And then this incrementally calculates the average. But at every step where we visit, the value estimate is always just the simple average of all of the returns at that state. And the idea is that once we start averaging this, we just have these, unbiased estimates of the value. And in the case of the Blackjack example, once you create the environment of Blackjack, which involves basically building this simulator, actually, where is the simulator? I guess I have the simulator defined here. So this like runs an episode, and there's these subtle details about like having a usable ace or not, and you got to make sure that all of the trajectories are correct. But in the end, you end up taking this policy that sticks. So like this is a pretty simple policy. It sticks on a sum of 20 or 21, otherwise it hits. And then this is showing that the value function converges, that there's less noise once you go out to 500,000 episodes instead of 10,000 episodes. So sample it. And then we did go over some of the questions about this for anyone that wants to review it. I mean, one question is, why does the value function jump for the last two rows in the rear? Yeah, and by the way, so one, like winning the hand gives you a reward of 1, losing gives you a reward of -1, and then a draw is 0. So yeah, like this value in the back here is like, it's pretty high. Like here it's like almost 1, and here it's like, between like 0.6 and 1. And then there is this like very sharp drop off where all of these states actually have a negative value. So which means that the player is actually expected to lose um, following this policy from these states. So yeah, usable ace. No, actually, wait. I think this. Oh yeah, yeah. So actually, yeah, and also if there's no usable ace, which is part of the state space, all these values are actually also lower than these values. So there's a few like things about this, and if you understand how blackjack works, it should be possible to give an answer to this. So I think I mean we already went over it, but does anyone want to or take a crack at explaining why the value is so much higher for these rows where the player sum is 20 or 21 in these rows, and then there's a sharp drop off right here where the sum is 19 instead of 20. Actually, in both cases, there's this drop off. Or yeah, I can just sort of go over it again if no one.
I mean, so at one point we compute the optimal policy, or like that's like something that happens later. And so you should be able to sort of compare this with the value function of the optimal policy. But what's like notable about this is that I don't know if you mentioned that, yeah, I mean you have it in that name, which is the policy only sticks on 20 or 21, right? So in some sense, like the step behavior of the value function here is probably of a function of the fact that the policy itself is sort of a step function in the sense that it radically changes the action that it takes, right?
Yeah, so at a sum of 19, this policy will hit. And
No, so it, or yeah, that's right. Yeah, sorry, hit. Yeah, that's a good point.
yeah, so I mean, it appears as though hitting at this sum leads to a loss more often.
On average, yeah.
So, you know, I mean, if I didn't have any further information, yeah, I would say that it possibly this is a poor action at this sum, and that is why it drops, and that sticking at 20 and 21 appears to be a pretty good action. I mean, if we change the policy, we could observe what the value was of hitting. Well, the value of hitting at 21 is -1
Yeah.
because you will always lose. And in fact, I don't even know if casinos allow you to hit at 21. I assume that they just sort of actually automatically end the game. Although weirdly for implementing this, you do have to consider the sum of 21 to be a state as opposed to a terminal state because I mean we do actually have like a value estimate here. And if you recall from earlier, the value estimate of the terminal state is 0.
Mm,
Yeah, a player sum of 21 is not actually a terminal state, at least just for convenience of implementing this as a, MDP. Which I think in something I did, I actually made that mistake of sort of not calculating the value of the sum of 21. But yeah, I mean, it is helpful to know that, yeah, sticking at 21 will be a win. It actually will not be a win 100% of the time because there is the possibility of actually losing to the dealer if the dealer has a natural and you don't, or having a draw with the dealer if both of you have a natural. And that is another sort of, depending on how you implement it, you could probably wind up with slightly different probabilities here. Yeah, and there's another question of why does it drop off for the whole last row on the left? Oh yeah, so that would be notice like these values are all lower than these values for both cases. And you could see like it's slightly darker here, or in the diagram in the book, it's a little, yeah, you could see the drop off here. And yeah, so this last row represents the case where the dealer has an ace showing. And I think we already went over last time, but it's like, it just means that if the dealer has an ace, it is just worse for the player than any other up card because the ace provides this flexibility of counting it as either 1 or 11. So that's why, this is just bad for the player. Also, having an ace is good because then if you get a face card, which is actually face cards are the most common card you could get. in blackjack, then they'll get 21 and a natural, and that's the worst outcome for the player. And then why are the frontmost values higher in the upper diagram than the lower? Yeah, so these are higher, and that's like, that like the player having a usable ace is just better than not having a usable ace. And that's why, especially with a sum of 12, especially. Because actually this means if a sum of 12 with a usable ace means two aces here. So this entire front row is the player having two aces in the case of a usable ace, whereas here this represents something else, like it could be a 10 and a 2 or a 9 and a 3, and that's not as useful as having two aces. Okay, yeah, and then we had this other question about suppose every visit. So the way the book lays it out is that as you go through the episode, you should only average the first state visited when you update the value, like in a given episode. And here, I'm actually not doing that. So I am updating, I'm going through the episode and I'm updating the value at state S every time it's encountered, as opposed to just the first time, which means that if I'm going backwards through the episode and let's say the state was the first state visited, and then I see it near the end, I shouldn't update I should wait until the very end to do it. And the question is for blackjack, suppose that we did it this actually the way I'm doing it instead of the way the book tells you to do it, which is the first visit Monte Carlo. Would the results be different? And we went over this briefly last time, but so the results actually shouldn't be different for blackjack because you never see the same state twice, because whenever the player hits or sticks, well, sticking will end the episode, so there's no additional state. But if the player ever hits, it'll actually change the state in a one way change. So you'll never actually see the same state more than once in a blackjack episode. So shouldn't matter. Yeah. And then, yeah, so this is sort of like the backup diagram for Monte Carlo, which is we generate this episode until the terminal state, and then we just sort of go back and collect all the data from it. Yeah, so then the next section doesn't actually have any, wait, does it have a question in it? Yeah, I guess it has one question, which is, let's say we're trying to estimate Q instead of V. So remember, Q is the estimate of action values instead of state values or state action values. So instead of having an estimate for the state, we have a value estimate for the state action pair. And in terms of the backup diagram, it's really like the same. Well, like we still run an episode until it terminates. It's just that the top of the, like this marks the start of the episode, and we actually care about the initial action taken for, and in fact, like, and then this one will also be, from here until the end, we'll also, use this estimate, and from here until the end. Here, it's the open white circles, which represent the states that we're interested in calculating the value estimate for. Yeah. So when we begin the episode with a state action pair, like we're not trying to, like here we actually sample different actions that are taken by the policy, whereas here, we're gonna actually keep track of which action and use that for indexing the estimate. So the point of this section though is an important point, which is that our goal eventually is to improve the policy. And if you look at the previous section, the way we improve the policy is by eventually selecting the greedy, hold on, do I have it in, hold on, I think I have an easier, right, policy. So eventually we want to improve the policy by sort of picking the best action that we know of at the time. And if we have the action value function, then we can just look at it and see which action is the best. If instead we have the state value function, we can still calculate this, but we're interested in the action that leads to the best outcome, which in this case is like leads to the highest value subsequent state. And here we actually have to calculate the probability of all the transitions. And this sum is actually Q. Right? So here, like if you do this calculation with V, you are calculating Q of SA. And we don't actually have this function anymore, at least in this chapter. So that's why, the argument is that it is more useful to estimate this than this. So does that make sense to everyone? Like that's sort of the main takeaway of this section.
Well, I think it makes sense that in order to approximate the action value function instead of the value function, given that we don't have the probability transitions.
Yeah, that is.
Or if
yeah.
we do have them, which in Blackjack you can theoretically do. Let's say for simplicity, just have those cards with replacement, or an infinite deck.
Yeah. Well,
it would
actually,
still be.
This does assume an infinite deck, the way this is simulated.
So
the probability of drawing a card is always the same.
Yeah, but that probability transition will be prohibitively large to compute.
Yeah. Well, actually, so the number of elements in it isn't that big because for Blackjack we have there are 200 states. So the size of the probability transition array would be like 200 times 200 times 2 times 3, which isn't that big. It's like a few 100,000 elements. But the hard part is mainly actually knowing the probabilities. Because like you have to know it's like, what is the probability that you have like, this particular sum, like you're here like in this state, and you need to know like what is the probability that if you hit, you'll win or lose or draw. So you need like each of those probabilities. And actually, the way I would calculate it probably is by simulating it and just collecting samples, which ends up defeating the whole purpose of having that function because, we're going to have to collect samples anyway doing this. But yeah, like you can calculate it explicitly, but it's a lot of calculations and like, someone did it a lot, like Thorpe did it a long time ago with but I think it took like hundreds of pages of I mean, he used the computer to calculate it, but even like writing down what the probability calculations are is like pretty difficult. Whereas writing the simulator might be annoying, but it's certainly you can do it within like, less than a page of text. So, then like, so the whole point of estimating the Q function is to do Monte Carlo control. And this, mimics the, generalized policy iteration, which is shown. I mean, this is sort of the diagram from the previous chapter, which is if we have the Q function, then we can improve the policy by following the greedy policy with respect to the Q function. And then we can reevaluate Q from the updated policy. And in the previous chapter, like here, this was like classic policy iteration where at every step you complete a full evaluation. So you start out with some kind of random policy, you evaluate the Q function for it, and this means like until it converges, whatever method you use, you fully calculate the Q function, and then you create the new policy from this. And then each time you do a full evaluation. Yeah, complete policy evaluation. And, then in the other extreme with value iteration, we actually don't wait for this to converge at all. And instead, we basically calculate the greedy policy after just having a partially completed evaluation of Q. And the argument in the previous chapter was that doing this back and forth, it still leads to the same convergence. And we basically don't have to wait for it to converge at each step. So yeah, I mean, whereas this diagram here. So we're sort of like marching our way towards both the optimal policy and the optimal value function. And you could wait for convergence at each step, or you could just partially evaluate V, and then at least to the point where the greedy policy would be somewhat different, because either way we're going to lead to the same place. And the other important thing from the previous chapter is that if we consider a policy, a new policy, which, at a particular state, instead of following the action of the policy, it instead follows the action that maximizes the Q function. So, we have this property, and then this means that the Q function, by taking this new action, results in having a value estimate at that state, which is at least greater than or equal to the value estimate of the state under the previous policy. And this was the criteria required by the policy improvement theorem, which was in this chapter, because the policy improvement theorem stated that if this is true, so like if we construct some new policy where the action value estimate at that state, taking an action under the new policy, is greater than or equal to the value of the state under the old policy, then that implies this is true. And it's, it's proven down here. So that means that if we go to every state and we make this change, then the new policy that we have, or like this like hypothetical new policy that follows this maximizing action at every state, actually its value function is superior to the old value function. And this proof sort of requires taking the leap that actually, because like the reason why this isn't obviously just true immediately is that when we first write this down, we're actually just considering taking this improved action one time. But like we're actually following the old policy for the whole rest of the time. But here we're actually saying that no, like actually if we take this different action all the time, like not just one time, then that actually is better. So yeah, like this, the sort of leap that the policy improvement theorem makes is that if the action is better just once that we take, and this is true at every state, then it's actually also better to take that action every time we encounter the state. And that is, the value function of the new policy. So yeah, well, so we're using the exact same policy improvement criteria, or we're just calculating the greedy policy. And going back also to the idea of the generalized policy evaluation, here the sort of breakpoint of when we're going to stop doing either step is a single episode. So we have the policy fixed for generating an episode. And then once we finish generating the episode, then we go through the process of updating the Q function and then, calculating the greedy policy again. And then the next time we generate an episode, we will generate it based on the new policy, which is the greedy policy. So, after this one episode, this Q function is not actually going to be converged to the action value function of pi, because all we did was, do a handful of updates to Q here, because like we only have this data. So we have this partially converged Q, but we can still, calculate the greedy policy with respect to it. And as long as we keep doing this and we encounter all the states and actions an infinite number of times, this is still guaranteed to converge. But this is only guaranteed to converge if we actually, from all these episodes that we generate, that we end up, visiting all the state action pairs an infinite number of times, which is, not necessarily going to be true. But if we use this method of exploring starts requires that every time we start an episode, we actually choose the state action pairs randomly from the entire state action space. So if we do this an infinite number of times, this actually does meet the criteria that we need for this to converge to the optimal policy. So yeah, let me just see then. So then this technique is then used to solve Blackjack. And, you're supposed to get a policy that looks like this, although depending on how many episodes you run it for, you won't actually get this exact policy, particularly for the case where you don't have a usable ace. Like here, so this actually matches, like this is the same as the true optimal policy. But here, like, I could like run this again and you'll see that it will, this diagram will change slightly. Yeah, there's still this, like, sometimes there's like a little notch here or something. But you can also see here that the value estimates are significantly higher than before or down, in this region where, the reddish color indicates these are actually expected wins for the player here. Like, some percentage of the time, it's more likely than not that the player will win. And in this case, the proper action here is to stick instead of hit, like the old policy was doing. And yeah, so in order to do this, like I am like initializing the episodes with like a random state action pair from here. And that's why, this is like able to converge. So are there any questions about the exploring starts method and why it works for getting the optimal policy? Okay, so then yeah, I mean, exercise 5.4 is just sort of the thing I already mentioned, which is that to average this, we need to maintain a list of all the returns observed for every state action pair, and that's inefficient. So then, in the previous chat, I think in like chapter 3, we already, or two or three, we already went over how to calculate this incrementally, and the formula is, I guess it's like cut off a little bit, but it's the same thing I have in the code, which is you can use the old return value and the counts, and if you iterate this, every time you have a new G, then this will end up calculating the average, just like this. And then we don't have to maintain a list of all the state action, of all of the returns for every state action pair. But we do need to maintain the count. So yeah, so we have the Q estimate, and we also have the count for every state action pair visited. Okay, so then the next section is just a slight alternative method to the exploring starts method. which is using an epsilon greedy policy, because in this case, for exploring starts, when we update the policy, we just make it a greedy policy. And the greedy policy will just take whatever action appears to be the best at this point in the Q estimate. And if we instead use an epsilon greedy update, then this maintains some small probability, or depending on whatever epsilon is, of taking random actions. And that also ends up guaranteeing that we visit every state action pair. Because like even if we initialize an episode, you know, like even the initial action we take, if it's epsilon greedy, will have this property that there is some probability epsilon of taking a random action. It may take a very long time of sampling to generate that, but you know, it's just an alternative way of maintaining the convergence condition. And then there's some proof here showing that, because like there's a little subtlety here, which is that the optimal policy that we end up calculating here is going to be the optimal epsilon soft policy rather than just the optimal policy without any constraint on it. And this just ends up proving that the policy improvement theorem still applies to epsilon soft policies as well. But here I mean, this is an example of running it with an epsilon of 0.1. And it's, you know, you still have the same issue where like, well, this is running for like 1 million episodes. And, you know, you can see like, depending on whatever, like, so if I change this epsilon to like 0.01, then it'll have like worse results because this epsilon, at least for 1 million episodes, is probably just too small to like, you know, accurately sample everything. And whereas like if I make the epsilon like really high, like 0.5, then we end up getting, yeah, so some of these estimates, this actually, oh yeah, so this actually means since there's only 2 actions, this means there's a 50% chance of taking a random action. So now we're at the point where there's no longer like hit or stick as like a defined, like a clearly defined optimal action here, because like half the time we're actually going to randomly hit or stick. I guess you can still see the outcome. This is, oh yeah, like negative 0.5 or 0.5. Oh, because the way I'm calculating this plot is I'm here, actually here. So this matrix is actually what the policy is. So yeah, you could see now that these probabilities are meeting the constraint of the 0.5 epsilon. So like here, this means that this first action will be taken 75% of the time and this 25% of the time. But if epsilon here was instead, you know, a much smaller number, this would be close. Here, like I'll change it again back to 0.1. And now this is, you know, like 95 and 5. So a little more straightforward. But yeah, like the policy that it ends up finding will still have this epsilon restriction on it. So this method is a little bit like you do have to select this epsilon parameter, which may be a problem if you're not really sure what it should be and don't have a good way of picking it. So yeah, those 2 methods are sort of the extent of the, you know, usual way of using Monte Carlo to find the optimal policy. So any questions about this whole first 4 sections of the chapter?
Well, you know, the difference between the exploring starts and the epsilon greedy policy in order to maintain the randomness, in order to guarantee convergence, makes sense to me.
Mm-hmm. Okay. Yeah, I mean, yeah, the only thing is like you have to select the epsilon, which is an extra parameter. Okay, so then this is so the next section is about off policy prediction. And this is like considerably different because now we're going to have a behavior policy. And I think it starts out with just prediction. Yeah. So we're starting off with prediction again, rather than finding the optimal policy. And the idea here is that we want to be able to predict the value function of a policy, but we want to generate samples or trajectories using a different policy. And the challenge is, how do we use the samples from the behavior policy to actually calculate the proper estimates? And the solution here is importance sampling. And the reason why it's called off-policy learning is because the actual behavior we're able to look at is not the policy that we care about. So again, like as usual, we start off with the prediction problem. And there is this important detail that the behavior policy has to cover the policy that we care about. So like there has to be some probability of the behavior policy actually doing what the target policy does. So there can't be an action that the target policy takes at a particular state that the behavior policy does not have any probability of taking. And the reason for that is because these ratios end up being used to compute weights that we adjust the average with. And you can see here that the probability of the behavior policy taking an action is in the denominator of this ratio. So if this was ever 0, then this would be, an undefined value. And that's a problem because then we can't compute this. The numerator can be 0, which means that the behavior policy took an action that the target policy would never have taken. And that just means that this product will end up being 0, which is fine. But we can never have the, this be 0 in the denominator. So, the
So does
important
that
sample.
mean,
Yes.
so does this mean that the policy that's going to be eventually generated is basically the result of the behavioral policy and then basically multiply by some matrix, well, not matrix or vector of how important, well, of how important each of those behavior components were essentially, or am I incorrect in that assumption?
Well, I mean, well, first off, in this part of the chapter, it's just defining this ratio. But like this ratio is, well, there's this probability here, which is, so this is the probability that a particular trajectory would have occurred under the target policy. And we need to compute that then in order to correct these estimates, right? Because we need to, so the claim here is that if we have the returns under the behavior policy, then the expected value of those returns, as long as they're multiplied by this ratio, will end up being an unbiased estimator of the value under the target policy. But yeah, so these end up correcting the fact that the returns we observe, are not, they don't actually match what we would see under the target policy. But yeah, so this importance sampling ratio is, yeah, it's just the difference in the probability of the trajectory happening under the target policy divided by under the behavior policy. So like if you observe a trajectory which happens to match the target policy, but it's very unlikely under the behavior policy, then this will be a very large number, because that trajectory is representative of what we want, but we wouldn't expect to see it very often. So it's basically just saying that, like, you need to, like, let's say it's like 100 times, less likely to occur. Then whenever we observe it, we should weight it 100 times higher. And that's sort of like, it's trying to create the samples so that they would match the samples we observe under the target policy. So like, if we were watching this under the target policy, we would have seen this type of trajectory 100 times more frequently than we're seeing it under the behavior policy. So we'll weight it 100x. And then similarly, if you have the opposite case, where there's something which is very likely under the behavior policy and it's unlikely under the target policy, or even has a zero, like if it has a 0 probability under the target policy, then we're not even going to count it in this expected value, right? It's going to be weighted at 0. And that should make some sense, that like, if there's some trajectory where, because like the G that we calculate is based on all the observed rewards to the end of the episode. So if there's stuff that happens at the end of the episode that does not represent the target policy at all, so this is like a 0 probability action, then we shouldn't use that data at all, because like the return value at the end, whenever it took a different action, like there's no way we can correct that to get a valid estimate, because like that contains 0 information about what we would observe under the target policy. Now, actually, there is some information, because it's possible that earlier in the trajectory, there would be rewards that would represent the target policy. Because like, if even one action occurs near the end of the episode where this is 0, then this entire thing becomes 0. So we throw out all the information. And that's because like the G value becomes sort of polluted by what happened at the end. And there are like more elaborate ways to still use some of the information if that happens, but for now we're not considering any of that. And notice, like, if we don't correct with these weights, then what we would end up calculating is the value function of the behavior policy, not the target policy. So does that make sense to everyone, that like, since we're collecting samples from the behavior policy, if we just sample normally, or if we just average normally without these correction terms, we would just end up calculating the value function of the behavior policy.
Yeah, well, yeah, that makes sense if there isn't that corrective factor, which is why I was thinking about the basically having the behavior policy times element-wise multiplication of a vector that's based on the relationship between the target policy and the behavior policy.
Well, I mean, like, practically, this will be calculated sort of in order as we go through the episode. We'll keep track of this weighting term, because like, and like just like what we did before, for calculating G. Here, let me just see where the pseudocode is for. Where do they have the off policy? Oh, I guess they don't even have pseudocode for. Oh, here. Yeah. So this is for off policy prediction. And you can see here again, we're going to go through the episode backwards. We're going to keep track of both G and W. And W will be updated at every step by this ratio of probabilities. And there's also this, yeah, well, we'll see. So there is a difference here. We sort of skipped ahead, but there are 2 ways to compute this. And so with ordinary importance sampling, we're gonna, compute this expected value by averaging G with all the weights. And just like a normal average, we end up dividing by the number of terms we have. Right, so this denominator represents the number of terms. And, each one of these things is itself an unbiased estimator of the value that we care about. Right. I mean, that's not, I guess it's not proven here, but yeah. And there's a problem here, which is that like remember I said, if you have a trajectory, which is 100 times less likely under the behavior policy than the target policy, then we're going to take the return we observed and weight it by 100. And, the expected value of that, because of all the times that, or like the expected value of doing that with all the trajectories is this, but, that particular value obviously won't represent any kind of return that is normal because it's like 100 times the value. But the point is that after averaging all of them together, we do have an unbiased estimate. But one of the problems with this method is that it can be high variance. So there's this alternative called weighted importance sampling, where the denominator is actually the sum of all the weights instead of the number of terms. And this actually, it's a little subtle because like this is actually not an unbiased estimator of this. This is actually a bias estimator. And you can see that by the fact that if we only have one term, like let's say, we only have one sample, then these sums disappear because we only have one sample. And this cancels out with this, and we have G. Right? And this is the G that we observed from the behavior trajectory. So this, I guess my Adobe is crashing, but this G is then, the expected value is actually the value of the behavior policy, not the value of the target policy. So that is the initial bias of this estimate. And that bias goes to 0 as we collect more samples, but it is initially biased. But the reason why both of these end up converging, because like it looks like here we just have a totally different denominator, but the numerator is the same, right? And the denominator here is the number of terms, and here it's the sum of the weights. The thing that sort of saves this and makes it work is that, here, let's say that there is a term where the weight is 0. Then this term will be 0 up here, but we're still going to count it in the denominator. So like if we have two terms and one has a weight of 1 and the other has a weight of 0, then one of the terms is not going to contribute to the numerator. But there'll still be a value of 2 in the denominator. Whereas in this calculation, if we have two terms like that, then we would have the same numerator, but the denominator would actually have a value of 1 instead of 2, because right, the 0 weight isn't going to count in the denominator. So that's sort of why like these look like they couldn't really end up being equivalent, but they end up being equivalent just from that little subtle difference that you have to deal with the case where there are 0 weights. Yeah. So then I'm trying to think, what is the first, oh, I wish this wasn't. Here, well, we should look at the exercise that deals with importance sampling. So this exercise, I actually have, they don't show it in the book, but this is like kind of a diagram of the MDP that we're talking about. So it's an MDP with a single action, and there is some probability P of transitioning back into the same state. And then there's a probability of 1 minus P of hitting the terminal state. And then once we, there's a reward of +1 on every transition. So the question is, suppose you observe one episode that lasts 10 steps with a return of 10. What are the first visit and every visit? Oh, you know what? Actually, this exercise has nothing to do with off policy stuff, does it? But we didn't, I guess it's in the section. Well, it's still a good exercise. This is just the difference between every visit and first visit estimates. So what are the first and every visit estimate of the non-terminal state? I do have it written down here, but if you're just like trying to think about it, so there's only one state and one action. So all we're thinking about is just you know, the reward samples that we have. So I guess you could start out with what is the first visit estimate of the value? Because remember, for the first visit estimate, we only consider the first time a state is visited in an episode.
Then it should be 10.
Yeah, it should be 10 because the start of the trajectory, we eventually have a return of 10, and we would use the first estimate. And then versus, you know, the every visit estimate in here. It's a little hard to say it, but you end up, so if you use every visit estimate, we have the state visited 10 times, and then we have the future return. So we basically have a list of returns, which is 10, 9, 8, you know, down to 1. And we have to average these together. So the average of this is just 5.5.
Which is the exercise number.
Yes, that's true. I guess that's probably intentional.
Yeah.
Okay. So then there's in terms of using this importance sampling weights, the example here is we're going to try to estimate the value of a particular blackjack state. And the policy that we care about estimating is the original one, where we only stick on 20 or 21. So in this state, you know, this policy will hit in this state, the target policy. And the behavior policy we're going to use is the random policy. The random policy just hits or sticks randomly with equal probability at every state. Yeah, so here, let me see how this. And there's some, yeah, so this is demonstrating the difference between weighted and ordinary importance sampling in estimating this state. And the claim is that the weighted importance sampling has lower variance, meaning that, you know, the mean squared error from the true state is better. No, so this is sort of a close estimate of what the value is. And this is just calculated by actually just collecting samples from the target policy. So this is what the value should be. And actually, here's what I did here is this is what the value of the state is with the random policy. So instead of, it's actually a higher value, I guess, because the random policy is actually a little better than the behavior policy here, which we saw earlier that the decision to hit on sums of like 18, 19 is pretty bad. So that's why the value's higher, the behavior policy. And then here, so this, if you like because like the variance is high, this part of the plot is gonna like change as you keep running it. But the idea is that these early values using ordinary importance sampling have a pretty high error rate compared to weighted importance sampling. There is a relatively lower error. Although honestly, like both of them actually don't like once you get out to this number of episodes, both policies have already, converged in a similar way to the correct value. I'm trying to think, yeah, like because you kind of wouldn't be confident until you get way out here, and way out here, the policies have very similar errors. But like where this becomes a major problem is when you have infinite variance, which is the subject of the next example. And the next example is this other MDP where we also have just one state, but now there's two actions. And if we go right, then the episode just terminates with a reward of 0. And if we go left, then there is a 10% chance of terminating with a reward of 1, and there's a 90% chance of returning to the same state with a reward of 0. And the policy that we're interested in is the policy that always goes left. So you should be able to see here that if the policy always goes left, then either it's going to keep going back to the same state, and eventually it will terminate with a reward of 1. So, the value of this state under this policy is 1. Now, the behavior policy instead is the random policy. So it'll go left or right randomly. And the behavior policy will actually have episodes that terminate with 0 reward in the case of it going right. So you can see here that so remember what the ratios were. The importance sampling ratio is this. So we basically have 1 over 1/2. Like every single one of these terms is going to be 2. So the longer the episode, like we take the product of these terms. So like an episode that's of length 1 has a weight of 2, and then there's a weight of 4 and 8 and 16. And if we happen to observe an episode that goes really long, then this will exponentially grow. And that is what the problem is, because if you look at the distribution of weights that we see, these weights are completely unbounded. And they're unbounded in a way where this distribution of weights has infinite variance. And the impact of that is that when we calculate, so these are showing calculations of the value with ordinary importance sampling. And although they do converge to a value of 1, there is no, like these spikes that occur. So like you could see like this black line was sort of converging to 1, and then it spiked up, and then it converges to 1 again. But there is no number of episodes that you can take that will eliminate these spikes, because you could always observe a weight which is large enough that it would dwarf like the n in the denominator, right? Because like this, like in the denominator of the average, we have a value of like 100 million. But the problem is that the weight could be like 1 trillion. And if you just add a weight of 1 trillion to this, you're going to get a very large spike regardless of how many episodes we have. So here I'm showing the same thing. Actually, this dotted line is calculating the same thing with weighted importance sampling. And the nice thing about weighted importance sampling is that as soon as we observe an episode that terminates by going left instead of going right, then the value of that estimate will just be 1. And we're like, those are the only terms that will contribute here. So the estimate will just stay at whatever it's initialized at. In this case, it's 0, until we observe an episode like that. And then as soon as we get a single sample that is useful to us, meaning it has a non-zero weight, then we just always have an estimate of 1. So, I mean, this is an extreme case of this method working, as opposed to the Blackjack case where we just had sort of a high variance early on. Here, it shows like in an extreme case like this, really weighted importance sampling is the only viable, method to use. So are there any questions about this example? The infinite variance example? Okay. This exercise is just asking for how would you do, so equation 5.6 is the weighted importance sampling equation. And the question is just how would you do it for action values? And I don't think there's much to this other than just all of the things that, like, this represents all of the times that we visit like the state of interest here. And the only difference here is that I'm just calculating the times of the state action pair being visited instead of the state. And there is another subtle difference here, which is that we don't actually have to use the ratio for the first action selected, which is why here I have this index of t plus 1, because here we're interested in the Q value of the state action pair. So it's irrelevant whether the action was likely or unlikely to be taken, because we're including it in the probability. Like, we just care about the value of this action, whether or not it's likely or unlikely. In fact, it could even be impossible under the target policy, but like we still want a value for it. So I don't know if anyone else had a different thought about this, or I don't think there's anything more elaborate for this calculation, but or any question about this? Okay, so this question is actually kind of interesting. I'm not sure if anyone else has an answer for this. I think I know what is going on here, but the question here is that although the weighted importance sampling has lower variance, there is this like feature that it actually starts out low error and then it gets high a little bit and then it starts converging again. And the question is, why does the error first increase before decreasing? Yeah, so I do have some answer to this, and it's kind of like in the weeds of how things are implemented, but does anyone have a idea about this? Or
I mean, would you be able to, I don't know if this is what your solution entails, but it seems like sometimes you can parameterize the explicit bias of an estimator in terms of the sample size. And like, in some sense, you could like show that like maybe the bias actually is going to potentially increase, or I suppose like it will eventually converge to, so it's a consistent estimator, so it should eventually converge to 0, but it not necessarily monotonically, right? Like that's like a very strong criteria for an estimator, right?
okay, so actually useful for that idea is that this is actually the value estimate under the behavior policy, negative 0.254. And this is the value estimate under the target policy, negative 0.277 something. So actually the bias here is quite low compared to the errors we're seeing here. So yeah, I don't think the issue here is the bias, because I think the actual bias here, like the error you would see from this bias is like way down here.
Okay.
Does that make sense? Also, like the bias should start at whatever it starts at, and then yeah, I guess maybe it doesn't. I mean, I guess if the bias converges to 0, I mean, even here, right, like this would be the most biased. So and then the bias, if it's not monotonic, then I guess you could argue that the bias starts out low because like the initial bias is just this difference. And then if it's not monotonic, maybe it grows. However, I don't think that is what this is the reason for this happening. But yeah, the bias is one idea. So I think the thing that's happening here is that we did so when you do weighted importance sampling, there is this subtle thing that if we do ordinary importance sampling and we don't have any non-zero weights, then this will be 0, right? Yeah, because the numerator will be 0, and we'll divide it by like 1 in that case. In this case, if we actually have no valid samples here, then we have to use some initial value. And in this case, they're saying if the denominator is 0, then just set this equal to 0. And here, in the case of Blackjack, yeah, we're going to we don't need to worry about that case because the denominator is never going to be 0. It's going to be 1, 2, like whatever it ends up being. So there is this initial value here, and if you end up taking this method, and let's say the initial value is 1 instead of 0, then the curve ends up looking like this. So then you don't see any kind of increase or decrease. And I think that the reason why you see this happen is because imagine that so this is for 100 runs. Let's like take a typical episode here. It turns out that if we just do one episode, there are quite a few episodes that won't have a non-zero weight. So there's some percentage of, in fact, I think I have it up here somewhere, but what is, I'm not sure where it is exactly, but maybe I wrote it in my answer. But there is basically going to be a majority of the episodes here will not actually have a valid sample, and our estimate for them will just be 0. And then we end up adding more estimates, but the variance of the like one sample estimates is pretty high. It's much higher than the variance out here. But the ones that actually haven't received any data have a very low variance. Well, they have, a 0 variance. And they just happen to be initialized at a value of 0, which is not very far away from the true value of negative 0.277. In fact, yeah, you calculate what the mean squared error of this is. It's basically 0.277 squared, which is not that high. It's a little bit. So this is a value of 0.168. And what is actually 0.277 squared is 0.076. So we basically here have the average of all the 0 values, and then however many of the episodes have, a high variance value. Actually, a value of either 1 or -1, probably. And, once we start filling in these values, we fill them in with values of 1, -1, or 0, but most of them are going to be 1 or -1. And if you look at, for example, if you take 1 minus 0.277, squared, this is a higher error than the value of 0. And even this -1 is also higher. Actually, it should be plus because it's a negative thing. So yeah, we have errors of like either 0.52 or like 1 point something. And those are actually higher errors. And the difference with I'm trying to think. So, but there was, yeah, for I don't even know if I answered this probably for ordinary importance sampling, but the main difference is the values that we actually fill in early on are gonna have an average value of this, but they end up being 1 or like, because we're dividing by the weight in the denominator, they either have a value of 1 or -1. And that's going to be as bad as it gets. Whereas for ordinary importance sampling, even a single sample, it could have a weight of like 10 or something. So that's why, even early on, even with the 0 values that haven't been updated yet, the values that are filled in have, a very high variance. Whereas here, all we have is the initial bias, which is very minimal. So, and what happens here is by the time we get to 10 episodes, almost all of the runs have a value filled in. And it just happens to be that the variance of having one sample that has a non-zero weight is a higher variance than just having all the 0 values that only have an error of, this 0.076. So I think that is what's happening. You can verify what I did here is initialize it at a value of 1. And the initial value doesn't affect ordinary importance sampling at all, because we always have the return value. Whereas for weighted importance sampling, we actually need an initial value. So that is what I think is going on. Does that make sense?
Yep. That makes complete sense, actually. Yeah.
Okay. Suppose it's oh yeah, so then okay, exercise 5.8 is a little mathy, but it's just it's asking for this example of infinite variance. The proof they use is a proof assuming first visit Monte Carlo, and they calculate this. And this is just asking if it's every visit instead, and I believe it still has infinite variance. You could look at this solution, if you want, but it just involves doing similar things to this. You just have to add up all the terms, and there just happen to be a lot more terms because you have to, for every lane, like here the lane 3 episode, this is just the first visit of the state, whereas here you have to actually add up all the weights for an average them for each of the 3 visits to the states, right? And you end up having a weight of 8, 4, and 2. But you should end up with the same solution, which is that you have infinite variance. So yeah, every state does not save you from this example. And here, let's see, what is, oh yeah, this is just a question of using the incremental implementation of the, yeah, we already went over this in a previous chapter. Yeah, this is just from section 5.1 even. And yeah, this is just the way to incrementally calculate the average that we had before. It just keeps repeating. It's the same thing. Let's see, divide. Okay, yeah. Exercise 5.10 is just a derivation, so we don't have to go over it now, but you can look at it. It's just asking to derive the weighted update rule, which is this rule here. So this is incrementally updating the value with, this is using weighted importance sampling. And it's just asking like, so this is the definition of the average. And then this is, the incremental way to update it. And there's a way you can prove it, but we don't have to go over it now, or we could go over it like another day if anyone is interested or had a question about the proof or found a problem in my proof. Derive the weight of the rule. This, yeah, right. This is just the same. Actually, no, this is the first time they show code for off policy prediction, right? Because previously they mentioned it for the value function, right? And this is just showing what it is for the action value function. And it's almost the same. It's just that, right, instead of keeping track of the state value samples, we keep track of the action value samples. So we could keep going. Well, I don't know, usually at 8, like people have to leave. Maybe we should leave the off policy control for next time. I mean, I don't know how people feel about continuing, or if there's just any question to go over for what we've done so far. But
I mean, we could, I'm fine with either way. If we wanted to like finish out the
okay,
chapter, or
depends
if
on
we
if, yeah, do people, okay, well, we can keep going until like, I guess some other people need to leave. But I mean, the idea behind off policy control is just that we already have a way of estimating the target policy from the behavior policy. And then it's just the same as on policy control, because we end up just forming the greedy policy using the Q function. And we just have to make sure that the Q function that we calculate is using the right, importance sampling from the behavior policy. I guess this also solves another problem, which is that previously we had to make sure we visited all the state action pairs, and we were trying to optimize, find the optimal policy. Here, we can just use a behavior policy that has coverage of all the state action pairs. And that way we don't have to worry about that sampling problem. But we still have the advantage that hopefully if the Q function is correct, we can actually calculate the greedy optimal policy instead of, having those other constraints that we had before. But so here it's showing using weighted importance sampling because that has lower variance. And we just have to make sure that we collect, enough episodes for it to work. There is this question here and here where we update the importance weight. And the question here is, notice that in the numerator, there's a value of 1 instead of the probability of the target policy. And the question is, why? Like, why is this a 1 instead of pi a st? And there is, an answer to this. Keep in mind, this is being used to calculate, the weight going backwards from the end of the episode. And remember that the weight is the product of all of these ratios. So does anyone have, and oh, actually, and this is here. This is the off policy Monte Carlo control on the Blackjack question. And here I'm using the random policy for the behavior policy. And you can see it does mostly work. I mean, it's the same problem where you need like a lot of episodes, enough samples to get an answer, but it's recovering mostly the same solution. It's not perfect. So yeah, for this, anyone want to take a crack at this for why the 1, there's just a 1 in the numerator instead of the pi?
Did you want me to give my solution, or?
Sure, you could just say your answer.
Yeah, so this is because in this case, the target policy should be like the deterministic policy effectively. So effectively the probability, you can like think of that as the probability of I of t being exactly equal to 1 and the probability of any other action being equal to 0. Is
Yeah,
that
so because we're creating the greedy policy, yeah, it's totally deterministic, which means that pi will either be 1 or 0. Yeah. But what about the case where pi is 0 then? Because here
well,
it's
so
only 1.
yeah, so that would be handled by the if statement above.
Yeah. So I mean, if pi is, well, actually, we could actually allow this to be 0, but then there's no updates that occur because the weight is 0. So you can see once W is 0, there are no updates to Q.
Yeah,
So we
exactly.
basically wait until W would be 0 and then just stop the updates. So that's
Right.
why. Now, weirdly, in my code, that is not the case. Here's the W update. So I actually do have the pi star
Yeah.
in the numerator. But the reason why I have pi star in the numerator is because instead of doing this, like let's say that there were two Q action values that were equally high, then the optimal policy is actually equal probability for both actions. So this just allows for the possibility of having like, so you either have to break ties, wait, consistently. I'm not sure what that means actually. Break ties rant.
I think that just means that if you break a tie in one direction, you have to break it in that direction for also, like always. So
Yeah.
I think
So
that's
in my case, instead of breaking ties, I'm just creating a stochastic policy that has equal probability
okay.
of the optimizing actions. Yeah. So yeah, this is how you would do it if you were actually taking the argmax. But if you are not taking the argmax and instead you are giving equal weight to all optimal actions, then you do have to use this. And you can still terminate when the weight is zero. Although I don't think I even do that here. But yeah, once the weight is zero, there's no need to continue the updates, regardless of what method you use. And then there is this programming exercise, which is just an example of how you would actually this exercise isn't really related to off policy learning because the idea is just to solve it however you want. But this exercise, it just sets up these tracks and it's this discretized problem where there is here, well, I'll just show you. There are these velocities. So these are the only possible velocities that the car can have in both the X and the Y direction. And then or yeah, I have the speeds. And then these are the actions. So the actions just represent changing the velocity in either the X or the Y direction. And you can only change it by a value of 1. Or you could, not make any change. And the idea is just you update the position of the car. And if the car would happen to like cross outside of the track, then it starts again at the starting line with a random position and no velocity. So that is the setup of the environment. And I guess in terms of using Monte Carlo, calculating the probability transition function for this seems like, again, it would be easier to just have a simulator. Although I do suspect for this problem, the probability transition function might not be that difficult either, because you do have some determinism. They do say that there should be a 10% chance of also inaction not actually changing the velocity, which is just another thing to add to the simulator. And this is just, I mean, if you want to practice like implementing stuff, this is sort of could be a fun exercise to see if you can write the simulator properly. But I do have here the tracks. So this is like each track. And I define the tracks here by like a set of points. So there's like the start, the finish, and the body of the track. And then, I have a simulator that checks if it crosses outside the track and that kind of stuff. But so here is what it looks like if you do the random policy. So I define a random policy. The random policy will just, take a random velocity change. And you can kind of get statistics on the policy. So like here is the random policy on track 1, and it takes about 1,100 steps for it to finish. We could actually repeat, or wait, no, not. Will this generate? No, this will end up generating. So here I'm generating the random run with a random policy, and you can see, it's thousands of steps to finish. Track 2 is actually a little easier to finish randomly. It's actually usually less than 1,000 steps. So here, what I'm showing is the black arrows are the velocity of the car, and the red arrow is what action is being taken. So here is, I did this with a few, so just for completeness, I used all of the different methods in this chapter, but this is the off policy solution, actually only running for 1,000 episodes, right? Which is not very long to do this training. And the question is, how does this do after 1,000 episodes? And the answer, so these are the statistics of the off policy compared to the random policy. And you could see that the off policy solution so far anyway is actually worse than the random policy. This is the distribution function. So this is showing the percent of episodes that finish in less than this number of steps. So you see the off policy solution, like the median is like, what, like 2,000, or like, oh, so for the random policy, it's 1,600 steps. And for the off policy, it's like 2,000 steps. So this method at least is not working for this number of episodes. And it's the same situation on track 2. So there's not really any improvement here. And I would say, like, the reason why this isn't working is because it's very slow to learn, because I'm using the random policy for the behavior policy, and we saw earlier that it takes like thousands or hundreds of steps to complete the race. So even running this, like, look, I run this for 1,000 episodes, which is not very many, and it takes like 3 seconds to do this because each episode is very slow. But if you compare that, like here it's exploring starts method. So here, 1,000 episodes, and look, this is only like 200 like milliseconds or 300 milliseconds. And that's because after the first episode that completes, there is some, learning that occurs. And then the policy here, like, we're following the target policy, which is trying to find the optimal policy. And immediately it's much better than the random policy. So each episode is much faster. And eventually, it's like, this is finishing the race in 15 steps, or this isn't that great. But like we can see that it's finishing the race in a reasonable time. So the learning is much faster. But I mean, that's not the only reason why this method is bad, because actually, even when I gave it, like, this actually learns a good policy after 1,000 episodes. And the off policy learning version didn't even learn a good policy after 1,000 episodes, even though I let it run for 1,000 episodes, which took, what is this, like 100 times longer? Or it is 3 point, or I guess, what is it, like 10? I guess it's only like 10 times longer. 100. I mean, it's like many times longer than this. So yeah, like, so this is exploring starts, which for this environment, exploring starts isn't that bad to implement. All you do is just start the car at any random spot with any velocity and have it take any action, and you end up getting a successful solution after 1,000 episodes. So this is the distribution of the of the policy that it found. And you could see that, it's in a pretty narrow range compared to the random policy, where like the worst outcome is finishing the race in like 100 something steps, and the best is 15 steps. And this is for track 2, the same situation. It works on both tracks. Yeah, and I had done this before, allowing it to run for like 1,000,000 episodes or something. And actually, while we're looking at I can run this for more episodes while we're looking at the other solution. But this is the epsilon soft solution, which with a value of epsilon of 0.01, and this also works. So in this case, I'm always starting the episode at the starting line and following the target policy. And here, even with a pretty low epsilon, it has enough coverage where it can successfully find faster solution on both tracks. But, the difference here is that you do have to actually pick the value of epsilon. So for this method, all you have to pick is how many episodes you train it on. And there's just like less to define ahead of time. Whereas, here we do have to pick this value of epsilon. And I did also add this little thing where I found for doing a really large number of episodes, you can like decay epsilon over the course of the run. So you could start epsilon at a high value and eventually lower it to 0. And that's another way of sort of ending up with a good greedy policy, even though you started out with some finite value of epsilon. But here I found that this value of 0.01 is pretty good for a very small number of episodes. But if you train for like 10, 1,000 or 1,000,000 episodes, the value of epsilon that is good here does change, and it gets larger. And it also changes if you end up decaying it. So depending on what environment you're using, sometimes it could be a problem if you have to pick more parameters, because there's no way of knowing ahead of time which epsilon is a good value, other than just, trying it a bunch of trial and error. Luckily, none of these training runs take, that long. Like here, 1,000 episodes only takes like, 1 to like 300 milliseconds. So, but, it could be a lot worse in general. So yeah, those are like three methods. The off policy method, I couldn't really get to work. And I think in practice, it would probably take a lot more episodes for this method to work. Yeah, I don't know. I did try it for a lot more episodes even than this, and it still wasn't really much of an improvement. So this is still. So any question about the different methods here, or like how the results end up being? Or was there, because they should cover all the techniques in the chapter, right? There was the exploring starts, epsilon soft, and then the off policy learning. Or did anyone else have a different method that worked on this? Yeah, I think training this for like 10 million episodes or something, it was, for this track, finishing in like 11 steps is like the best you can do, I think. And it was able to find that like pretty consistently. I think I was also kind of punishing with the simulator with going off track, because just for simplicity, I just like take the starting point and ending point of a step and like make a square. And if any part of the square is like outside the track, I consider it off track, as opposed to just like the diagonal line. So it is like the worst case scenario of going off track. I think I think if there's another exercise that's worth talking about in this chapter, because this is like another heavy math one showing the importance sampling. And then this is another, this is like, again, like similar to the previous one, where it's almost the same. It's just updating something for state values to state action values. And I don't think there's much to it, again, other than, changing the time steps to keep track of the state action visits, and then also not using the importance sampling ratio for the first action that is taken. Because that's what I did before in the other exercise as well, because we don't need to calculate the ratio of action A, because that is already, that's one of the inputs to the Q function here. And I think you can also see that in the implementation of the. Actually, I think I did both versions of estimating for off policy prediction. Yeah, so when you do off policy prediction with V, with the value function, there is, I'm trying to think, for the update step, there is this difference in the order of which you update the weight. So here you update the weight immediately, and then the count, and then whereas when you do it for the action values, the weight actually doesn't get updated. Wait, where's the weight update? Oh yeah, here. So here's where I update the weight, and it doesn't get updated until the end of this step, and that's just reflecting the difference that when we do the last update, which is the start of the episode, or wait, no, here I'm actually going through. Hold on, when do I update the? AQ. Oh no, I guess I am going backwards through it. But yeah, there is this like subtle difference of when you don't use the first important sampling weight with Q, because you have to make sure that when you're calculating the actual Q estimate that you don't worry about the probability of taking action A in the case of the QSA estimate. But yeah, so I think that this finished doing what the racetrack. Which one did I? Okay, so now this ran for, geez, a lot of episodes. And actually, yeah, so now, oh, I guess the high end is still, well, now you could see that the minimum is a little lower at like 13 episodes. But yeah, some of the trajectories are still kind of bad. This is for, I guess this is, wow, is this actually for 10 million episodes? Yeah, I guess. Yeah, exploring starts. Well, anyway, I was surprised for this method that even after just 1,000 episodes, it could actually learn pretty well. Because there are actually, if you do, because there's 7,300 states, right? And there's 9 actions. Is that right? So there's actually like a lot of state action pairs, like far more than 1,000. So even after just 1,000 episodes, the exploring starts method actually works pretty well, which I was surprised because I would think you would need at least like a large number of samples for every state action pair, but it turns out it actually works even with just 1,000 episodes like this. But yeah, so I don't think for this chapter there's any other exercise really worth going over. Oh, crap. So I don't know if there's any other question or anything else to clarify, but yeah, I think we could just move on to the next chapter next time if there's no other question.
Yeah. Sounds good to me.
Okay, well, yeah, I guess, yeah, we can stop here.
All right.
Sounds good.
Thank
Thanks
you.
for coming,
Yeah.
everyone.
Yeah,
Yeah,
thank
if
you.
there's any, and yeah, the notes you can always see at the, in the meetup description, there should be a link to these notes, which you should be able to go to just here. And then this static export should work for everyone, where you can't like run the notebook, well, unless you download it, but you can see online just all the notes and the code if you want. So yeah. So if you want to go over the more mathy solutions, you just go to that website.